Good afternoon. So today's lesson is quite important. We're not going to deal with complicated problems. You will see the actual math stuff we're going to end up computing because we're going to do lots of examples during the lecture. These examples are quite straightforward. What is not straightforward is the connection with the concept and the main idea on how to establish a boundary value problem involving partial differential equations, in particular, in this case, the heat equation. So what is extremely important is to go slow and make sure you really understand how you connect the description of the problem and the conditions verbalized, using regular words, with how you establish those conditions using the notation corresponding to the equation itself. It's important because it will get much easier later, since you will keep on using these types of conditions for various problems, and it will become second nature. But for now, when you're new to this, it's very important to make sure you understand how you set up the conditions and how you can relate the result with a physical phenomenon. We're going to deal with the steady state temperature in the one-dimension case, which is extremely easy to imagine. Well, not extremely easy, but easier than most other examples. So you can make a connection to see if your answer makes sense from a natural or physical point of view. So once again, it's very important not to rush to the computation and say, oh, I understand how you get that calculation, because that's not really important. It's the interpretation what's important. So let's review, let's write down again the heat equation in Cartesian coordinates. And this time around, we're going to deal with the heat equation in one dimension. So U denotes the temperature of the object. And the object of study here is the one-dimensional object in which heat flows either left, right, or right-left. So heat flows horizontally only. I think I didn't mention this last time. I forgot to mention because to really make it a one-dimensional heat equation in this format, just with these parameters, we assume that the object itself, so let's say these are the boundaries of the object. At x equals 0, the left endpoint, as is commonly the case, and L, the right endpoint. So basically, the space variable x is between 0 and L. So that's the object here. So to make the equation look the way it looks, just ut equals kuxx, we also assume insulation on the long side of the object. So basically, we assume that there is no heat transfer along the object. It's basically like an insulated wire. So another analogy is to imagine an insulated wire, either of negligible thickness, or if it has some thickness, you assume that there is no heat propagation in the cross section of that wire. So that's why we assume that heat only flows left to right or right to left. And remember, by convention, the positive flow of heat energy is to the right, to make it analogous to the positive semi-axis. So really, the only way heat enters the object are through the sides. At x equals 0, at x equals L. So x equals 0, x equals L, identify the endpoints of the object. All right, so how do we write some boundary conditions attached to the equation? Well, basically the boundary conditions will have to say what happens at the endpoints. The only way heat enters the object is through the endpoints. And you can specify those conditions either in terms of temperature or heat flow or flux across those endpoints. You may also need to know, of course, what's the initial state of the object. So let's actually establish that first. In these problems, we always have an initial temperature distribution. So what is the initial temperature, which is to say at time t equals 0? Well, because the temperature depends on the location of the object, then an initial condition or an initial temperature distribution for the heat equation will be in the form of a function. So you will say that u of x0, so notice u of xt is the temperature of the object at location x and time t. So therefore at time 0, the temperature at location x will be given typically by a function of x. So this function is typically given in the actual problem. So for instance, let's say you have an object that is it's hotter to the right hand point than on the left side. Okay, so an example could be to say u of x0 will be x squared. Knowing that x equals 0 is the left endpoint, that'll mean that the left endpoint is at temperature 0 Celsius, let's say. And let's say the length of the wire is L equals 10. That means the right endpoint is at 100 degrees Celsius, right? Because it's going to be 10 squared. But it can be really any function, and that function actually will play a crucial role in connecting it later on with the Fourier series, but we'll still have a long way until we get there. So let's hold our horses on that so far. So initial condition or initial temperature distribution in this case, as the name implies, is the actual function at time 0, but that's not typically a constant. It can be a constant, but it need not be. It's typically a function with respect to x. When we solve the problem itself later, this is the stuff you're going to deal with at the end. Then, like I said, you have various conditions on the actual boundary of the object when x equals 0 or x equals L. And these boundary conditions can take various forms. You can have, for example, prescribed temperatures at endpoints. So for instance, you could say, I want to keep the temperature at the left endpoint at 1 degrees. So this is translation for keep the left endpoint at 1 degree Celsius. So notice that this implies that this is for all time t. So throughout the process, as we run the experiment, we want to keep the temperature at the left hand side. So that means that x equals 0. But for any time t, we want to keep it at 1 degree. By the way, if you imagine how that will look like, and it's useful also to imagine how the device will look like. You don't have to be a mechanic or an engineer to really do that. Just imagine a plausible machine. You know, if I have, just look at the right corner here on the object, okay? So how do I keep the temperature at 1 degree? Because remember, once, you have a certain temperature on both sides of the object here, the temperature flows in both directions, from hot to cold and back so the temperature changes in time in general. But you could imagine, for example, a device right here on x equals 0, that as soon as the temperature, let's say, wants to go above 1 degree, the device will remove heat to the exterior so that it brings it down to 1 degree. If the temperature drops a little bit below 1 degree, then the device will bring in heat to raise it to 1 degree. So imagine a device that basically kind of adjusts itself by adding or removing heat energy on that surface so that the temperature is kept at 1 degree. That's one way to imagine this. And let's say for the same problem, I want to keep the right-hand side temperature at 5 degrees. So the right-hand side is going to be U of L T equals 5 degrees. L being a given number, right? The length of the wire. So that's the right-hand side of the space domain, right? For the the space coordinate. So that's the same as saying keep the right endpoint at 5 degrees Celsius. So basically a fully formulated problem that should be sufficient to, should contain everything I need to solve, will contain the boundary conditions, which in this case are in the form of prescribed temperature and an initial condition. So we don't need to we don't need to use mathematical tools at this point to really believe that this is a correctly formulated problem, because we kind of know from the physics of the situation that this is all I need to be able to solve the problem, and then the solution has to exist and be unique, right? Because we have an initial temperature, so we know that information, we know what happens at the endpoints. That should be sufficient to describe the full process of how the temperature changes in time. So that's an example of a fully formulated boundary value problem. Or BVP. And another type of problem is when you specify, for instance, what type of heat transfer happens across the surface. By the way, there are lots of different types of boundary value problems, not just these ones. So there are there's lots of variation. And the boundary conditions usually are the ones that dictate the type of solution you're going to have to deal with. So you could have prescribed flux or heat flow at endpoints. So for instance, you could say that, let's say you have a positive, let's imagine this is the object, again, between, with x between 0 and L, and let's say that heat enters to the left side, and in the amount of, let's say, 5, the units, remember, this is a flux, so this will be heat energy per surface area per unit of time. I'm not going to write the units here, but it will be units of energy, heat energy per surface area per unit of time. But let's say it's going to be positive flow, so the one that enters the object. And then let's say we'll also have heat entering on the other side in the amount of equal to 1 unit. Now remember, the heat flow is going to be positive to the right and negative to the left by convention. And also remember that whenever you refer to the flux or the heat flow, you have to use the Fourier law of heat conduction. So the flux at location x and time t is equal to the minus big K, which is the conduction term, times u partial x at xt. So never forget this Fourier law of heat conduction, because you must refer to it when you write the boundary conditions in terms of the heat flow. Because never confuse, of course, the flow with the prescribed temperature. So here we don't specify a specific temperature at endpoint, we just specify a constant influx or outflux. In this case, it's influx on both directions, on the left endpoint and on the right endpoint. So the boundary conditions, take a look at how they look like in this case. Remember, positive flow from left to right. So on location 0, so on x equal to 0, and at time t, the flux will be equal to 5. I'm going to write it with a positive number, 5, because it's from left to right. But on the right hand side, that means at location L and at time t, because the flux is in the opposite direction, I'll take it with negative sign. So minus 1 means enters to the right hand side. Plus 5 means enter to the left hand side. Because if you write it plus 1 on that location, that means it will leave the object instead of entering the object. Which can be, depending on the problem. But the way I show the problem here, it will be heat that enters from both the left and the right hand point. Now, you need to write these boundary conditions in terms of u. So replace phi of 0t with minus k u partial x at 0t, which is equal to 5. And then minus k u partial x at lt equals minus 1. So here the boundary conditions will be u partial x at 0t equals minus 5 over k, and u partial x at lt is minus 1 over minus k, which is 1 over k. So k, remember the conduction term is given or can be found from various other data in the problem. So this is another boundary value problem correctly defined if you have this description of what happens on the left endpoints, or on the left and the right endpoint. And you can have a mixture of this. You could have a prescribed temperature on one endpoint and flux on the other endpoint. Or other conditions like, for instance, the Newton law of heat exchange, which we'll talk about that later. Really the sky, I mean, not the sky's the limit, but there's quite a variety of boundary conditions that can be established. For the vast majority, these are the two types of conditions. Prescribed temperatures prescribes fluxes at the endpoints. There's a name for these type of conditions, but I'm not going to overwhelm you with that right now. I want to do the last part of the lecture with examples of steady state temperatures. So stay tuned for the next page. All right, so the steady state temperature for the one-dimensional heat equation. So remember again, we have the insulated wire, endpoints are 0 and L. Maybe in one of those examples, actually, let's just skip. See, I can use an actual number for the length, but you will see that it's easier or it's better to keep it unspecified, like a given length L, because I want to make some comments which will be more suggestive if I leave the length unspecified. So remember, L is the length of the object. So therefore, X is between 0 and L. And normally the temperature depends on X and T. But remember, in the steady state case, we assume that eventually ut is equal to 0. So eventually the temperature doesn't change with respect to the time t. And in that case, the question is, what is the steady state temperature? What is the eventual temperature with respect to X? So when that happens, and I really emphasize the word when that happens, or no, if that happens, that's the key word here. If that happens, that steady state temperature can be solved by setting the Laplacian equal to 0. But this is one of those rare moments in our class in which this is actually a very simple equation, because if, to begin with, my temperature depends just on X and T, and therefore, if we assume that it doesn't depend on T anymore at some point, as T goes to infinity, then we reach a state in which U depends only on the space coordinate X. So basically, the steady state temperature in the one-dimensional case is just a simple differential equation, ordinary differential equation. So this becomes an ODE, an ordinary differential equation. So you could even replace uxx equal to 0 with u double prime of x equal to 0. So how do you solve this equation? You just integrate it twice. So let's just solve the steady state temperature, and then we're going to play with various boundary conditions. So if u double prime of x is equal to 0, we can integrate twice, and each time we have a constant of integration. So u prime of x is going to be the integral of 0 dx, which is just a constant. Let's call it m. And if we integrate it one more time, the integral of m dx, that's going to be m times x plus n, which is another constant. So the steady state temperature in the one-dimensional case is just mx plus n. It's just a linear function. So enjoy it while it lasts, because in other cases, of course, it won't be that easy if you have more than two variables. So basically, if I have an object that depends on two space coordinates, like a plate or a 3D object, obviously the steady state temperature will be a PD in itself, because it will depend on more than one space coordinate. But in the one-dimensional case, it just depends on x. Now here comes the part in which I really want you to basically imagine what happens with the heat as it circulates in the object for various boundary conditions. When I'm going to formulate the boundary conditions, again, I'm going to drop the t variable. So the goal here is now to solve this steady state temperature with appropriate boundary conditions, but we're going to drop the t variable because, again, we are under the assumption that the temperature doesn't depend on t anymore. So we're solving for the limiting temperature. It's important to point this out. We're not solving for the temperature at a given time t. We're solving for the steady state temperature, which is what happens as t goes to infinity. So let's say we use prescribed temperatures on the boundaries. So let's say in my first example, I'm going to write the object again here. Let's say I want the left endpoint be kept at temperature 6, and the right endpoint I want it to be kept at temperature 1 degrees. So I want 6 degrees here and 1 degrees here on the left endpoint and the right endpoint. X equals 0, x equals L. So in that case, let's see, let me make it, yeah, that's fine. So in that case, we have to find the constants m and n, right? So therefore the conditions are u of 0 equals 6 and u of L equals 1. And remember, the steady state temperature is mx plus n. So we simply plug in the boundary conditions and try to find m and n. So we have a system basically. U of 0 equals m times 0 plus n equals 6. And then u of big L, which is the length of the object, is m times L plus n equals 1. From the first equation, we get that n equals 6. We substitute it in the second equation. And big M is equal to minus 5 over L. So the steady state temperature will be minus 5 over L times X plus N, which is 6. Okay, so if you were to sketch this temperature with respect to X, if X is 0, it's going to start over here from 6 degrees, and then it's going to be a decreasing function. If I replace U with L, obviously it's going to be 6 minus 5, which is 1. So it's going to drop up until 1 here. So at this point, I wanted to think about and understand why it is basically logical or to be expected that this steady state temperature has this shape in the form of a decreasing function. Because remember, if we model a real life phenomenon, the solution has to make sense. And just to understand the process or how this equation works, is a good exercise to check it against reality, essentially. So let's go back to the object here. Remember, the heat flows left and right, right and left. And by the way, it doesn't matter what the initial temperature is, right? This is the long-term behavior, right? What happens if you keep the edges, the left end point at 6 and the right end point at 1. So no matter how much back and forth you're going to have with the temperature inside the object, at some point, by keep on adjusting the temperature so that it's always 6 on the left and always 1 on the right, clearly there's going to be higher temperature as you come closer to the left end point. So that area is going to be hot. And clearly you're going to have lower and lower temperature as you approach the right end point. Because remember, the heat tries to flow from the hot to the cold end point. For example, if initially you have, let's say, a very hot point on the right end point, well, because you kept that temperature at 1 degree, there is a lot of removal of the heat on that end point, so then essentially it's going to dissipate eventually. So it's not a surprise that when everything stabilizes, you're going to have basically a steady drop in temperature from the hot end point to the cold end point. So it's not a surprise that the steady state temperature will be in this form of a decreasing line. So that's one thing. Now, let's see what happens if you have, for instance, another condition in which we mix things up. Let's say I have a prescribed flow on the left end point and a fixed temperature on the right end point. So let's say I have, in the second example, and I'm going to use the same domain, right, 0 and L. Let's say the flux at the left end point is going to be 6. So it's going to be a positive flux inside toward the object. So heat flows in like this. And the right end point is again kept at temperature 1. So U of L is equal to 1. So here is again kept at 1 degree. And before I even solve for the constants m and n, so the same question, what's the steady state temperature? Let's see if we can analyze a little bit and see if we can predict what happens with the overall temperature distribution. So I would say that things are probably kind of similar to an extent, with one difference, that you keep on adding temperature, heat energy on the left-hand side. So essentially on the left-hand side, there's no removal of the heat. You keep on adding on the right, but in order to keep the right-hand side at temperature 1 degree, obviously you're going to have a lot of that device, which keeps it at 1 degree, will have to remove a lot of heat that comes from the left-hand point. So I hope that makes sense. While the heat energy keeps on entering from the left-hand point, the only way that device on the right-hand point to keep it at 1 degree the only way to do it is to constantly remove the heat. So the temperature distribution is going to be basically similar. It's going to basically drop as you come closer to the colder end point. But there will be a little bit of a difference compared to the previous case. And let's see what happens if I solve for m and n. Now with the flux, you have to be careful. Remember, the formula for the flux is going to be minus k, and I think I have to give you actually what k is in this case, just to make it simpler. So it's minus k, the conduction term, times u partial x at xt. And for this particular problem, let's say big K, the conduction term is equal to 2. So therefore, if I drop the t, because I'm looking at what happens in the long run, then the flux is going to be minus k times u partial x, or minus 2 times u partial x. So therefore, if I go back to the boundary condition, the flux at time 0, so phi of 0, is going to be minus 2 u partial x at 0. That should be equal to 6. Now remember u, go back here to this square here, remember u is mx plus n. right? So u partial x in the one-dimensional case is just equal to m. The derivative with respect to x, that's just the constant m. At any time t, there's nothing to plug in 0 for. So that's going to be just minus 2 times big M equal to 6. And therefore M is equal to minus 3. And then the second boundary conditions, u of L equals 1. U of L, that's going to be M. So u of big L is again M times L plus N equals 1. M is minus 3. We just determined that before. So big N, the other constant, is 1 plus 3L. So the steady state temperature now is going to be minus 3 times X plus N, which is 1 plus 3L. And I can pull out 3 just to make it easier to interpret. 3 times L minus X plus 1. So let's focus on this steady state temperature. To an extent, it's very similar to the one before. And if you were to sketch it, let me see if I can squeeze in a little graph here. It will start from the high point at x equals 0, it will be 3L plus 1. And as x is equal to L, so as it goes down to L, the temperature is going to be dropping to 1, right? So that this is going to be 1. All right, so look carefully. What's the major difference between the two cases? Because the only difference was in the previous case, the left endpoint was kept at 6, and now the left endpoint has a constant flow of heat equal to 6. It's a different units, right? 6 degrees, these are 6 joules, whatever is the energy unit measure, per unit of time, per unit of area, and so on. Well, it's clear that in the previous case, if you have prescribed temperature 6, then clearly it starts from 6. But this seems to be the case, in the second example, it seems to be that the left endpoint stabilizes at a temperature that kind of depends on the length of the object. It seems to be that the longer the object is, the hotter the left endpoint is. Now, does that make sense? And the argument is it makes sense because if you have a very, very long object, right? So imagine you have a really, 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 really long object. By the time the heat energy reaches the right endpoint where the heat is removed, there's a lot of energy accumulating on the left endpoint. So there's a higher temperature at a stable, at a steady state level. When t goes to infinity, the longer the road is. Because remember, in this configuration, the only way heat leaves the object is through the right endpoint. So the longer the object is, then the more hotter the left endpoint gets before the energy is removed from the object to the right endpoint. So please don't rush this type of discussion, and maybe rewind and ask questions during the office hours if this doesn't make sense, because it's important for later. I'm going to finish up with a quick example just to show you how sometimes you won't be able to find a steady state temperature, and when you look at the boundary conditions, it should be obvious why you are not able actually to find a steady state temperature. So stay tuned for the last page. All right, so let's take a look at these two examples. Let's call them, I wanted to make it a single example, but let's just say there are two examples side by side, 3 and 4. So I want an example in which the conditions are in terms of flow, not prescribed temperatures. So in the first case, let's draw again the object. There's a left flow inside the object, which is equal to 5, and left flow out equal to 1. So again, just remember, in both cases, we're looking for the steady state temperature. So we're solving for the linear function mx plus n. It's just the question to find m and n. So keep in mind the signs, right? Both fluxes by our conventions are positive because they flow from left to right. But that means the one on the left comes inside the object, the one on the right leaves the object. So essentially the object gains, per unit of time, gains heat energy to the left endpoint and loses heat energy to the right endpoint. So let's pretend that we don't know what happens in the long run, although if you look carefully and you spend a minute to think, you might realize what happens overall as t goes to infinity. But let's just say we just do the computation. We assume that, ut equals 0, and then we're solving for the steady state equation, which it gives us this, right, by integrating it twice. Now the boundary conditions, again, at these times are in the form of a flux. So the flux at 0 is just going to be minus k times u partial x at 0. That's the Fourier law of heat conduction, which is equal to 5. And the flux at the right hand point is minus k u partial x at big L, which is equal to 1. Now remember, u partial x is just m in this particular case. Doesn't matter if it's at 0 or L. So because ux is equal to m, the first equation is minus k times m equals 5. And the second equation is minus k times m equals 1. So on one hand, we have m equals minus 5 over k. And on the other hand, m equals minus 1 over k. These are different values. They can't both be true. They cannot have the different value at the same time. So basically, the steady state equation does not have a solution. But what I'm interested in to discuss at this point and to make you think about for a moment is to see why that's the case and why it was actually incorrect to begin with to even solve the steady state equation. Because the steady state equation is under the assumption that eventually the temperature stabilizes, which is to say that eventually u partial t equals 0. But does that happen in this case? I mean, is it the case that as t goes to infinity, does the temperature not change anymore as t goes to infinity? And the answer is no. The temperature does not stabilize. Right? And why that's the case? Well, because the energy gain, the heat energy keeps on increasing. The temperature keeps on rising because the inflow is higher than the outflow of heat energy. You heat up more on the left than you remove heat on the right hand side. So obviously this object heats up indefinitely. Now, of course, in practice, something is gonna break. It's gonna melt, whatever, something will happen. But given this configuration, and when the assumption we make about this object and the material and how the heat flows, left and right, right and left, and so on, this heats up indefinitely. So, of course, there's not gonna stabilize in time. So u partial t will never be equal to 0. So it's not even correct to formulate the problem. But even if you don't realize that, by solving the problem, you reach to a situation in which cannot be true, which is a signal that the problem is not correctly formulated. In this case, it was not correct to assume, given these boundary conditions, that u partial t is equal to 0. And in some other cases, the reason is a little bit different, but still the the steady state equation doesn't have a solution because it shouldn't be formulated in the first place, or the boundary conditions might be incorrect, as you will see in the next example. So I hope that's clear on this case, why we don't have any solution. Let's see what happens if we simply reverse the left flow with the right outflow. So in this case, we have an object And you should pause the video after I do this to see if you can figure out why, the reason why we don't have a solution for the steady state temperature. All I'm changing here is that the inflow is 1 and the outflow is 5. I simply reversed the values from before. So, you know, the situation is very similar. Phi of 0, the inflow on the left side is going to be 1. The outflow on the right hand side is equal to 5. I mean, same problem. And you may wonder, why did I bother actually to write it if it's the same situation? And pause for a moment and ask yourself, so again, we can't solve the steady state temperature, because m cannot be both minus 1 over k and minus 5 over k. But pause the video for a moment and see if you can spot the difference, because if you look at this, you know, it's a bit different than before in terms of what happens as t goes to infinity. And assuming that you just pause the video and figure out this, let's see actually if the boundary conditions are actually do make sense in the first place. Because I mean, in this case, there's going to be a net loss of heat energy. So that means eventually the temperature should drop basically to 0, right? If there is a net loss of heat energy as t goes to infinity, because 1 comes in, 5 comes out. In the previous case, it heats up indefinitely. Here it's cooling down indefinitely. But in this case, of course, the idea is that if that's the case, if it's cooling down indefinitely, you won't be able to remove this amount of heat energy as t goes to infinity. So at some point, the boundary conditions themselves are incorrect, right? You can't remove, you know, that heat energy in the constant amount equal to 5 as t goes to infinity. So you cannot do that indefinitely, because at some point the temperature drops too much, so therefore that condition won't make sense at some point. So what I want to point out is that for the problem to be to be correctly formulated, the boundary conditions should be correct, which often it's not actually trivial matter. I mean, of course, in many examples it's pretty obvious, like with the heat equation, a physicist will figure out immediately whether the boundary conditions are correct or not. But in other cases, they might be more subtle, but the boundary conditions should be correct. And of course, whatever assumption you make about the long-term behavior should also be correct, because that's not always the case that the temperature will have a limit, for example, under the conditions of our problem. So I think that's it for today, and I'll see you next time.